Next, we have Jensen inequality. A function fx is said to be convex over an interval ab if for every x1, x2 belongs to a comma b and a certain value of lambda between 0 and 1. If this inequality is satisfied, then we say a function is convex. And what do we mean by this inequality is that, let's say we have a function. This is function and we have an interval a, b. If we have some curve here, let's say this point is x1 and this point is x2. So the right hand term specifies if we draw a chord between the 2 points fx1 and fx2, this is the function value at fx1, this is f of x1, and this is the function value at x2. So this is f of x2, and if we draw a line between the x1 and x2, so what it means that the function, any point, let's say this is f of y, so any point y in between the x1 and x2 will always lie below the chord connecting x1 and x2. So this, in short, is the meaning of this inequality. In other words, we can say if we take any other point on this curve, any other point at this curve, and the function value corresponding to that point will always lie below the chord, then we say the function is a convex function. And on the other side, if we want to see what if the function is concave, now if we take negative of the convex function, we say that the function is concave. Here fx is convex function, the negative of fx is concave. And from the picture we can say that, like this is the curve, if we have 2 points x1 and x2, and if we draw a chord between x1 and x2, so any point between the x1 and x2, the function value at that point will always be greater than the chord connecting the point fx1 and fx2. So this is the pictorial view of when a function is concave. So the best example for to identify the convex function and the concave function is x square. This is a plot for x square. So we can say that at any 2 point, the function value is always less than the chord. And for concave, we can say a logarithm function. If we draw any chord between the 2 points, the function will always be greater than the chord. And when the function is convex, if this is convex function, then from the Jensen equality, we say that the expectation of function is always greater than the function and taking the expectation of x. This is for the when fx is convex, and if fx is concave, then the equality becomes opposite. Okay, so this is when fx is concave function. And the classical example of this where the Jensen inequality is applied is in the capacity, because we know capacity is equal to B log 2 1 plus SNR. And if we want to take expectation of this capacity, we can write it as E B log 2 1 plus SNR. This is the left hand side, and then for the right hand side we can write B log 2 1 plus expectation of SNR. And since logarithm is the concave function, then the equality what we have is less than equal to. So that means we say that when we take the expectation of SNR, this is treated as the upper bound. And when we take the expectation over the B log to 1 plus SNR, this value will always be less than this upper bound. And from Jensen inequality, we can prove that distance between the two distribution Px and Qx is always greater than equal to 0. So is the information x comma y is greater than equal to 0, and the information in x and y given z is always greater than equal to 0. So now what we have seen, all the definitions for the entropy, joint entropy, conditional entropy, and mutual information, they were for the discrete random variables. But usually we have to understand, yes, we can easily translate the discrete random variables to the continuous random variable, but we will see some definitions corresponding to the continuous random variable. So for a continuous random variable x, we can define its CDF as f of x is the probability that a random variable x takes a value less than equal to x. And if fx is continuous and fx is differentiable, then we can easily get the probability density function of x. Here we have this PDF. In discrete case, we have probability mass function represented by P of x. And integration of minus infinity to infinity of PDF is equal to 1. That means the area under the curve for PDF is always equal to 1. What we mean by this is, let's say if we have this distribution between 0 and A, this is uniform distribution, and the area under the curve will always be equal to 1. So this value will be equal to 1 by A. And here, similar to that of discrete, we can have the definition of entropy. Here entropy is not entropy, but we represent it by differential entropy. And this is denoted by small h of x is equal to integration of f of x log of f of x into dx. For discrete case, when we studied entropy, we had h of x is equal to minus summation x p of x log 2 p of x. So for the continuous case, we are replacing this expectation by the integration and this PMF probability mass function by probability density function f of x. Now if we take the example for the uniform distribution, so this is the uniform distribution where the x is distributed uniformly between the interval 0 and A, and the PDF of the uniform distribution is 1 by A. Then we substitute the PDF of this uniform distribution into this entropy expression. We get 0 to A because the PDF exists only between 0 and A. So we have this 1 by A, log of 1 by A, and what we get is log of A. So for uniform distribution, we have entropy of x is equal to log of A. And since this A can be negative, can be less than equal to 0, so log of A can also be less than 0. And thus we can have a negative entropy here in case of continuous random variable. Whereas for the discrete random variable, we have seen that the entropy h of x is always greater than equal to 0. But here h of x can be negative. The next is normal distribution when x is distributed according to the normal Gaussian distribution with mean is equal to 0. When mean is equal to 0, we say it is normal distribution and is represented in this particular way. And if we substitute this probability distribution function into the entropy form, we get 1 by 2 log 2 2 pi e sigma square bits, since we are talking about log 2. Similarly, we can also say the joint differential entropy if we have set of random variable x1, x2, xn, and they are distributed with density f of x1, x2, xn. We can also substitute this density into the entropy form and we can get the joint differential entropy. Conditional differential entropy, let's say we have a pair of x and y with density f of x, y, then we can have this form: h of x by y is equal to negative integral of joint PDF x, y into log of p x, y dx dy, which can be represented in h x, y and h of y. This is same as in case of discrete random variable. So no need to understand this because this is similar to that of what we have studied in discrete variables. So next is the entropy of multivariate normal distribution. Let's say we have set of random variables x1 to xn that is distributed according to the normal distribution with mean mu and covariance matrix K. Then the PDF of x1, x2, xn is given by this form, which is the function of the mean mu bar, the covariance matrix, and this x bar is a vector containing x1, x2 up to xn. So mean is also a vector, mu1, mu2, and so on. And when we solve this, what we get is 1 by 2 log 2 pi e power n and mod of covariance matrix bits. So entropy in this case of multivariate normal distribution is a function of the covariance matrix. So since this was for real valued, and we need to understand for the complex multivariate normal distribution, because in channel we usually have complex values. So for complex case, we have the entropy as log pi e power n magnitude of covariance matrix. So similar to the discrete case, we can also write the mutual information I of x, y, which is the distance between the joint distribution of x, y and the product of the x and y. This is the relative entropy between these two distributions. And similar to the case of discrete, we have entropy of x, y is equal to entropy of x minus entropy of x by y is equal to entropy of y minus entropy of y by x. And there is an important result for this entropy. Let's say we have a random vector x that is a real vector, n-dimensional, and it has 0 mean and covariance k. So in this case, we need to find out what is the distribution that gives the maximum entropy. So the important result is that when we consider the normal distribution, we get a maximum value of entropy. So what we can conclude is, for the normal distribution, it maximizes the entropy, and for any other distribution, this entropy will be less than the entropy of the normal distribution. And this equality holds when x is 0, k, that is normal distribution. This implies that the Gaussian distribution or multivariate Gaussian distribution maximizes the entropy of any random variable with same covariance matrix. And this is for the real case. If we consider the complex valued, then we have the 0 mean circularly symmetric complex Gaussian random vector maximizes the entropy. So these are the two important results for the real valued and for the complex valued that are particularly considered when we used to study the wireless